In this module, we'll cover how you can model a feed system. The goal will be to review the different gate types and runner designs, as well as learn how to model feed systems. Why? It's critical to properly model gates and runner systems. There are several mold types supported by the Autodesk Simulation Mold Flow Advisor software. The first one being part only. This is just an injection cone on your part surface, so no feed system model. Good for preliminary analyses. Single cavity. It's one part with a feed system. We have multi-cavity, which could be the same geometry upon multiple cavities, or you could have a family tool. Now, when building a feed system, there is some logic within the user interface, so you have to follow these very specific steps in order to be successful. First, you select your mold type. Next, you place your injection cones. Then you set your parting plane. And finally, you specify your mold properties. Only after you've completed these 4 steps will you be able to start modeling your feed system. If you notice at any time that your icon you're trying to select is grayed out, that means you may have not followed this in this correct order. So take a step back and see which step you may have missed. Within the user interface, you'll see in the ribbon that there are runner system modeling tools. There's a wizard, as well as some manual tools, and the option to actually import runners or IGES curves as runners. So we'll cover each one of these in the later part of this presentation. So when modeling a feed system in Advisor, or even running analysis without a feed system, part orientation is absolutely critical. The orientation of your part needs to have the sprue pointed in the positive Z direction. So basically your intended parting plane on the tool is going to be the XY plane. This is necessary because it allows us to use the modeling tools for the feed system as well as to accurately predict clamp force. Now before you model your feed system, of course you bring in your part, and you may want to duplicate that part if you're going into a multi-cavity tool. So if this is the case, you don't have to import that part multiple times. You could use the cavity duplication wizard here. So you can see there are several options. You could have a grid pattern, a radial pattern, and then from there you need to tell us how you'd like that pattern laid out. Do I want a 2x3 layout or a 2x4 layout? So you have options to either draw that layout or just specify it in here and specify the row spacing between those. So we covered the duplication tool prior. That's very helpful if all your cavities are going to be the same in your multi-cavity tool. Well, what if you're doing a family tool where the geometry between each cavity is different? That's just as easy. So what you'll do is go into your application menu, and you'll notice there's an option to open and then add. And all you do is simply, after you've imported your initial model, you can do this process to add your second model. And then you can do this process again to add your third model, and so on and so forth. The next thing we'll look at is the parting plane tool. So the parting plane for the mold is something that we use as a reference point for modeling our feed system. So not all parting planes in reality are planar like this one. However, this is simply for modeling purposes within the software. So it does not have to exactly represent your parting plane on the tool or your intended parting plane. We can adjust the size of the mold blocks on the A plate and B plate a little later on. So here's where you specify or can change your mold plate dimensions. So this is critical because your A plate, or that pink plate there, is going to represent or be used to represent the length of your sprue. So the thickness of that plate should basically be the length of the sprue that you intend to model. Within here, or this window, you can also add a third plate if you're doing maybe a hot runner design. So you could put the floating plate in there. You can also change the mold material. Maybe you don't want to use a P20 steel. Maybe you want to use an aluminum mold. You can do that in here. You may also notice that in your mold properties, there's an option to specify an offset. This is basically allowing you to specify how far the mold plate should extend beyond the part's dimensions. When choosing a dimension for this, it's important to consider the rest of your mold design. So if you intend to build a feed system, it must be contained within this mold block. If you're going to add cooling lines later on, then this mold block should be large enough to accommodate those cooling lines. You must place an injection cone prior to being able to specify a parting plane, true or false. Your part should be oriented so that the intended sprue is in which direction. It's important to have the proper orientation to ensure which of the following. Now that we've covered some of the tools or some of the prerequisites before starting to model your feed system, we'll now cover some modeling techniques that you can use. There are really three main modeling techniques when building a feed system. You can use the runner wizard, you can manually model them, or you can import a feed system using IGES curves. When using the runner system wizard, we put everything in one convenient menu for you. In this menu, it'll allow you to automatically generate your sprue, runner, and gates. Let's say you just want to generate your sprue and runner and not your gates. Well, you can do that. Just uncheck the option next to create gates. If you didn't want to create your runners and just wanted gates and sprue, then uncheck the option to create runners. The rest can be modeled manually, and we'll talk about that a little later. You also have the choice of 4 different layouts. You can choose automatic, which will let the software do what it thinks is best. You can choose the block option, an H pattern, a star pattern, which is essentially a radial layout, or you can use the default properties or change them from this dialog. So you can modify what your cold runner is. Is it a cold runner, and what are the dimensions to that within this menu? There's also an option to test the intersections in your feed system. Runner System Wizard is a great tool. However, there will be instances where you need to model some of these features or entities manually. So to do that, you simply go up to your ribbon, and in this case, I'm going to click the Create Gate icon, which would populate this menu. From here, I just select the injection location I'd like to build it off of. I verify that the type is the correct type I want to use. If it's not, I can always modify it at this time by clicking on that icon to the right of type. From there, I can modify this cold gate to maybe a hot gate. Maybe alter some of the dimensions of that gate as well. From there, you just hit apply and you're done. Now we'll move on to creating a runner manually. So to do so, you'll go into your ribbon and click on the icon to create runner. Once you do that, you'll get a menu much like we see on the right here. This menu has several options in it, the first one being runner type. What's in there to start with is based off of your default settings. However, if you wish to change it at this time, you can do so by clicking on that icon to the right and then modifying these properties. When modeling a runner, you also need to specify naturally a start and end point for that runner segment. So you can do that here. You can do that by either entering coordinates, or you could click on, let's say, the end of your gate and then specify an endpoint that's maybe just off in the X direction, a certain distance. Some additional options you have are methods of connection between the runner segments. That's basically the 2 checkboxes you see below the endpoint. One is to auto connect to the next runner. So this is almost like a daisy chain. So you click on your first point of your runner or specify it, and then you could click on the second, and then when you make your third selection, it's basically going to build your next leg of your runner system based off that first one you built. So as you click, it'll just continue building off of one another. The second option there, snap to runner, is a good one if you have that on, because when you're hovering over a feed system or over a runner segment, that'll snap to it and make sure that you're actually connecting to it. Next we'll cover the final entity that you can model manually, and that's a sprue. So to do this, you just click on the icon Create Sprue, and you'll see it'll bring up a menu like you see on the right here. From there, you'll specify where the actual drop point is. So this is how your sprue is going to go drop into the tool through your A plate. You can use the grid to help you specify this if you wish, or if you know the exact coordinates, then use that. There's also an option there, a button that says middle of the mold. So let's say you have 4 cavities in there and you just want to put the sprue between those 4. You don't have to measure it out or figure out the coordinate system. Just click middle of the mold and it'll place it for you. From there, you have your sprue properties, which again, those are based off your defaults initially. However, if you wish to change it, you can click that icon to the right of type. Your length is not something that you change. You can see what the length is going to be in here, but again, when you created or specified your mold properties, you told us how thick your A plate was, and your A plate thickness is going to dictate how long your sprue is. From there, you hit apply, and your sprue will be created. Now we'll cover the final option for building your feed system, and that would be to import your runners. This can be very useful for complex runner systems that may have several curves to them. They can be more easily modeled in your CAD package than they can be within Moldflow Advisor. So we typically recommend this procedure in those cases. So to do this, you can see there's an icon to simply import runners, and we allow you to import an IGES, a UDM, or a .scy file. But please keep in mind, this is import runners. So after you import your runners, you're still going to need to build your sprue and your gates. One of the common pitfalls for people when they're importing IGES curves for their runners is that there are gaps between these curves. You should zoom in your CAD package to just make sure these gaps don't exist, because if these gaps exist, when you import them into Advisor, naturally your feed system is going to be broken and not connected at these areas. What are the available methods for creating a feed system in Advisor? This last section of the presentation will cover some additional runner modeling tips. Some of the topics we'll cover are how to edit properties, positioning the gate, duplicating models, modifying runners, manual gate changes or creation, and 3 plate molds. Even after you've created your feed system, you have the option to modify the properties. So to do this, there are really 2 ways. One is you simply click on the feature you wish to edit, and then right click and go to properties through your context menu. The other option would be to access the properties through clicking the property button in your ribbon. Once you're in this menu, you can see you can change several things. So in this case, maybe I want to change my runner type from a cold runner to a hot runner, or maybe the shape from a circular to a half round. I can do all that and apply these changes now. Let's say you've placed your injection cone and you now want to move that. Sure, you can delete that by clicking on it and hitting your delete key, or you can just grab it and drag it. If you have an exact location you like to place it, which is commonly what I'm trying to do, is you can actually click on it so it's highlighted, and then right click to access the properties through your context menu. The properties for an injection location will basically be the coordinates in space, so you can now modify your X, Y, and Z coordinates for it to move it. It is relevant to have proper gate positioning, because when you have your gate positioned properly or exactly, it will aid you in using the cavity duplication wizard as well as the runner layout. If you try to use these tools, things may become skewed if your gate location is not in its intended place. How the gate is created is influenced by the location of the injection cone as well as the position of the parting line. I'll show you some examples of how we can use these to create different gate scenarios. So some of the ones we'll cover specifically will be a submarine gate, or maybe a tunnel gate, you call it, a side gate or a tab gate, and a 3-plate or hot drop. So when attempting to model a submarine gate, or what some may call a tunnel gate, the parting plane should be offset from the injection cone like we see in the image below. When it's offset like this, we'll basically assume that the injection cone is the starting point of this gate, and that the other end of the gate will end on the parting line, because the assumption here is that the feed system is going to run along your parting line. So within the properties of your gate, you'll actually see additional options for specifying either a horizontal length or an angle to the parting line. So when trying to create a side gate, or what some may call an edge or tab gate, you want to make sure that your parting line is parallel to your injection cone. In this case, in your gate properties, you'll simply be specifying a horizontal length for that gate, so we know how long the land is on it. This is a good example if you're trying to specify a 3-plate or a hot drop tool. Again, your parting plane or parting line will be offset from the injection location as you see in the image below. That way, the vertical length will be defined by the distance between the injection cone and the parting line. This parting line, as you may have noticed in each one of the previous scenarios, is simply a modeling tool. So when you're creating it, it is completely planar, and that's okay, because again, it's simply a modeling tool. We'll cover some other ways you can model 3-plate tools in the future of this presentation as well. So even though we have a cavity duplication tool, please keep in mind that it may be necessary to rotate or translate your model after the fact. So you can see in the image on the left, the gates on the top 3 cavities are on the right hand side of the part, whereas on the bottom, they're on the left hand side. We may need to rotate these parts so we get a uniform orientation. Maybe not. On the right hand side, this scenario was caused more due to not precisely placing your gates like we had mentioned in previous slides. However, you could also technically translate these models or move them so the gates do line up. If not, the feed system would be skewed slightly when you go to model it in this case. As you may have guessed, there is a tool for rotating parts. In this case, you can see in the top scenario, we did our cavity duplication tool, or used that tool, to create 6 cavities. However, the top 3 cavities have the injection cone on the right hand side, whereas the bottom 3 have it on the left hand side. So let's change that for the top 3 cavities. To do this, you simply select those top 3 cavities that you wish to rotate. Then you go to your Layout Tools panel, and you tell us which way you want to rotate it. In this case, we're going to rotate it on the y-axis by 180 degrees. And as you can see, now all the gates are on the left-hand side of each cavity. Now we'll take a closer look at the second scenario. In this case, we didn't quite precisely place our injection cones before running the duplication tool. So we're stuck with some mismatched injection cones, and when we go to model our feed system, everything's going to be skewed a little bit. So hopefully we're not in this situation, but if we do get into it, there is a tool that we can use to align it. That's in your layout panel as well. You'll click that, and it'll just ask you which direction you'd like to align the tools in and which cavities. That's it. So let's say you have your feed system modeled, and for one reason or another, you decide you want to move a portion of your runner system. So this is easy to do. Within your feed system panel here, you can see there's an option to move runners. All you'll do is activate that. It brings the panel up that you see on the right hand side here. Once you see that, you can grab the end of the runner segment at any place and simply drag it and move it. Or you can edit the coordinates there to get a more precise placement. The one good thing to note is that when you do move these, anything that's connected at that point, say you have a primary and a secondary runner connecting up, it'll move both runners for you and maintain that connection. So you're not breaking your feed system by using this tool. So let's say you find yourself using a standard set of runner sizes. This applies for sprues, runners, or gates. What you can do is save these standard sizes and then load them later on for your convenience. If you find that your gates do not have the same z-coordinate, or maybe they have varying lengths, it's not going to be very easy to model this using the runner system wizard. So, what we would typically do is model this manually. A typical method might be to create your sprue using the wizard, and then create your gates manually. From there, you can create your runners manually, which would connect your sprue to your gates. There are some additional ways to model 3-plate molds that we'll cover here. How you model it or create these drops will really depend on the geometry of them, and even your user preference. A lot of times you can do it more than one way, so do what works best for you. Some of the methods we'll take a look at for creating 3-plate molds will be drop-in parts on a floating plate, the drop-in parts on a B-plate, and the parting gates on a B-plate. This will all make more sense in the next couple slides. Here's a common way to model a 3-plate mold where we put the drops and parts on a floating plate. This floating plate is enabled by that checkbox that I mentioned previously in this presentation in your mold properties. When you check it, this third plate will be present. Basically what happens is we'll run your gate from your injection cone up to the secondary split line. The runner will run along the secondary split line, and then the length of your sprue will still be defined by the thickness of your A-plate. One of the less common ways I'd say to create a 3-plate mold would be to put the drops and part on the B-plate. So in this case, you have your parting plane specified above your part a set distance, which would define the length of your drops. From there, your injection cone is on the part, and your gate runs from that injection cone up to your parting line. Your runner then runs along this parting line, and your A-plate dictates the length of your sprue still. This is the third way I typically see people model 3-plate molds in Advisor, where the part and gates go on the B-plate. In this case, you can see the clear advantage is that we can capture 2 degrees of taper on our drop. So we specify a parting line slightly above our part surface there. The injection location runs, or the gate runs from the injection location to this parting line to define that first taper at our nozzle. The next one goes through the floating plate, and that's technically a runner. From there, we go up to our secondary split, and you can see the runner runs parallel to that. Then again, the sprue will be defined by the thickness of the A-plate. In this case, this would be the only way you can model this scenario. The first 2 situations would not work. A precise gate location will aid in which of the following? Now that you've had an opportunity to watch this presentation, please feel free to try these exercises to further your skills. These exercises are ones that I'd recommend doing in particular, because this concept is best learned through practice. For further information on how to access these exercises, please refer to the introduction video.